So thanks for having me. I'm gonna completely switch gears now, and I will talk to you about the work my team and I are doing on characterizing other worlds from a single pixel. For a bit of background information on myself, I'm a theoretical astrophysicist focusing on exoplanets and brown dwarfs. In case you haven't heard about brown dwarfs before, they are like giant exoplanets, but more often than not, they lack a parent star. And I did my PhD in astrophysics in the University of Leiden in the Netherlands in 2013, followed by 2 postdoc gigs at the University of Arizona, Tucson, and UC Santa Cruz, before joining UCF and the Department of Physics as an assistant professor in 2019. Since I joined UCF, I have PI'd 2 NASA Roser proposals that were successful, and I will talk a bit about them soon. Hubble Space Telescope proposal, and I am also the co-I on successful ground-based telescope proposals and a James Webb Space Telescope theory proposal. As far as teaching is concerned, I've done a couple of different courses. I just wanted to draw your attention to the Introduction to Numerical Computing. We are trying to teach STEM students how to code in Python and how to actually do good coding. So code with comments, debugging, and all of this package so that it's ready to be given to any collaborator or your clients in the industry. If you have any undergrads that should learn Python, send them my way. And I also wanted to mention that I'm part of the United Faculty cohort for 2021, which is a great UCF program for newer faculty and gets us up to date with the newest pedagogical methods. Anybody interested in it should apply for it next year. It's a really good program. About the work I'm doing, we are focusing on exoplanets and brown dwarfs. And like the ones you can see up here, these dots are actually planets orbiting another star. And you can see that they occupy just a single pixel or less in your images. And everything there is to know about these worlds, if there's clouds in them, how do these clouds change, what's the weather in that world, is there a surface, oceans, is there life, is hidden in that one single pixel. And the work we are doing is trying to use a lot of methods combined to try to get as many information as possible out of that pixel. And the biggest breakthrough came about a decade ago when we started having the first time resolved observations from these targets, where with time resolved observations, what we're doing is we keep on staring at the planet as it rotates during one day around its axis. And because of different surfaces, different clouds coming in and out of you, you can actually see changes in the light you get from your target, like you see down here. For example, this is one target rotating in a single day around its axis. And then by using a combination of radiative transfer codes, retrieval algorithms, and mapping techniques, we can get the maximum amount of information from this single pixel and decipher what it is we're actually looking at. And my group works in pretty much all of these things and try to get the maximum information from that single pixel. So one of the things we're doing, for example, is adapting radiative transfer codes to make them more realistic so that we can better fit data from observations. And I just submitted earlier this morning one paper with our work on it, where we changed the atmospheric properties to be able to treat atmospheres in disequilibrium chemistry for the first time now. And we see that disequilibrium chemistry has a very big effect in the atmospheric properties of our exoplanets and brown dwarfs. And that will also affect clouds in the future, which is the next step we're going to be working on. And by actually adapting codes to be able to treat atmospheres with disequilibrium, we, for the first time, can fit our observations much better. So these triangles you see in these figures here are actual observations of brown dwarfs. And you can see the newer models we have is these blue tinted lines, and the oldest models are the orangey reddish lines. And you see, by introducing this equilibrium chemistry, we for the first time can actually fit our data. Areas where that doesn't work that well, like here, is because we're still missing the clouds, which we are going to be putting in soon. And clouds are very important in that particular region for our targets. The other thing we're working on in my group is polarimetry. And if you've never worked with polarization before, we are pretty much using the same physics that your polarized sunglasses use in order to study exoplanets and brown dwarfs. And polarization holds about 67% of the information of light. And so far we have been ignoring it, but the next generation of telescopes will be taking it into account. And with that in mind, I have PI'd two NASA proposals that were successful. And we're focusing on one of them on terrestrial planets. This is actually the Earth seen in polarization, you can see here. And we are trying to figure out in polarization, what are the key ingredients that make a planet habitable so it can support life, and how does it change when a planet is uninhabitable, like Mars or Venus? Can we use information from polarization to get extra information on the habitability of a planet? And my graduate student, Kenny Gordon, is soon submitting his first paper as part of this work. And the other project is focusing on giant exoplanets, so gaseous planets like Jupiter or Saturn. And we are trying to create a roadmap for the observations and characterization of these planets for the next decade and a half. What are the spectral resolutions we need to be looking at? What are the time integrations? What size telescopes do we really need to maximize the information we get for these planets? And of course, we have been characterizing these planets, but we can also map them to start placing constraints on the atmospheric dynamics. Back in 2015, I started the first mapping with an MCMC algorithm. And what we're trying to do is initially use likers like the one you see here and study how our maps change over time. And by studying the change over time, we can, for example, see the existence of banded structures like Jupiter's on the brown dwarf atmosphere. And that places unique constraints in general circulation models that then inform us directly about the weather in this world. And as part of this project, I have also been granted 15 orbits with Hubble Space Telescope. Unfortunately, my observations were just about to happen 3 days after Hubble broke down. You might have heard about it in the news. So they're delayed now by a year. But about April 2022, we should be getting 5 continuous orbits observed for Lumen 16A and B. And we will have maps studying how the weather changes in these worlds. Of course, atmospheres are not 2D, they're 3D, right? So looking towards the future, we have started trying to get information on the third dimension, so the pressure, the depth in these atmospheres. And the way we're doing this is by getting high resolution observations and different wavelengths probe different pressures in the atmosphere. This is really similar to what you experience from the Earth's atmosphere, where visible light makes it all the way to the ground. Infrared or most of the UV is blocked higher up in the atmosphere. So we're taking advantage of the same effect, and we can start creating better 3D images of the atmosphere. Like you can see the water band, for example, here probes really high up in the atmosphere. Alkali lines a bit deeper, and most of the continuum, which you see here, is deeper in the atmosphere. So we can map all of these layers and get a better 3D image of these atmospheres. As part of this work, I'm also part of the science team of a new instrument we're proposing, LIGER, which will be aiming to do it at an even higher resolution that current instruments are doing so far. Looking towards the future, all of these methods I introduced so far are working pretty fine, but they're really slow. We are mostly using codes written in Fortran, some Python as well. Some of the simulations can easily take a week to 3 weeks to happen. And in the James Webb Space Telescope era, with a lot of ground-based telescopes, large ground-based telescopes, giving us way more data than we can handle in high resolution, we will need to find ways to speed things up. And that's why we are looking into trying to use machine learning in order to adapt our retrieval algorithms and speed them up, and also create 3D maps of these atmospheres. Michael Himes, a grad student from Joe Harrington here at UCF, has already pioneered this work with using machine learning for atmospheric retrievals. And you can see here, he does a great job so far. And we're trying to use his expertise and any input we can get from computer scientists in order to get machine learning into the next step for us and start creating 3D maps in a fraction of a second that we can do so far. Further in the future, just to very briefly mention, there's still a lot of work to be done for improving our radiative transfer codes, including polarimetry from the very start, because it's very sensitive to the atmospheric structure, and the minute changes in the TP profile, temperature pressure profile, sorry, will change clouds and they will change spectra. So we are applying for funding and thinking of the future, trying to adapt our codes even further. And with that, I'm just going to finish with my acknowledgements. Thank you to the organizers for hosting me, and also my big network of collaborators, both at UCF and across the US and Europe.